So today, question?
I was going to ask a quick question about the format of quiz 22.
Oh, okay.
Just how would you go about describing a hyperbola?
Oh, okay. Well, first of all, if something's a hyperbola, you would say it's a hyperbola, which way it opens, maybe where's the center, you know. What you don't need to do is go into the foci and the asymptotes and all the details. If I'm asking you to identify a shape, and let's say it's a circle or a parabola or an ellipse or a hyperbola or a line, no matter what it is, identifying what it is the most important part. Identifying where it is would also be somewhat important. To get down into detail is less critical. Does that
right. Yeah, so you're not expecting us to address how steep or narrow the hyperbola is.
No, but if you identified something as a hyperbola versus a parabola, that's important.
All right.
That's really what it comes down to. There's going to be the opportunity, like the quiz you guys just turned in, where you're actually going to tell me the details. Okay, the center, the foci, the asymptotes, whatever's involved in the thing. Now, today we're going to be looking at the calculus of parametric equations, and it turns out to be extremely useful. And the question came up yesterday, you know, why don't we just do it this way in general? Well, no, the way we do things in general is the most efficient way, but all problems cannot be done the same way. So let's remind ourselves of the chain rule of derivatives, because that's what we're going to go over today. So if I have something of the form y equals f of g of x, okay, and then we wanted dy dx, we know that's f prime of g of x times g prime of x, and the g prime of x is the chain rule. I'm using function form. But what if I have something that looks like this? Y equals, y is a function of x, which is a function of t. Oh, okay. So I'm going to use, so I'm thinking y is a function of x, but x itself is a function of t. Then I always take the inner derivative. So the question is then, what's dy dt? This, by the way, is the exact same thing as this. F and y are the same things. My g and then x is the innermost. So the chain rule says that you do the outer one first. So this would be dy dx times what? Anybody? What would I multiply that by?
Derivative
dx dt.
Dx dt, exactly. See, this is function notation. This is generally referred to as differential notation. These are saying exactly the same thing, but it's the form I'm writing. Because if I write y and I have x-ish stuff, we say dy dx. If I write f of x and I have x-ish stuff, we say f prime of x. So now I'm saying y is actually a function of x, which is a function of t. So dy dt is dy dx, dx dt. Okay, what's the big deal? Then that means that dy dx is dy dt over dx dt. And this is the derivative formula for parametrically defined curves. Not because I told you, but because all we did was just apply the chain rule. Oh, okay. I applied the chain rule and then I solved for dy dx. So if I said y is a function of t and x is a function of t, and then I want the derivative, this is exactly how we're going to do it. So let's do a simple example of this. Grab my eraser here. Okay. So let's start with something relatively simple. Let's say that x is about t squared plus 2, and y is about 3t squared minus 1 cubed. Let's make it kind of complicated here. What is dx dt? What is dy dt? So dx dt, first of all, would be what? Anybody? That should be easy.
Just 2t.
2t. Dy dt, well, that would be So I'd have 3t squared minus 1 to the second times 6t using my chain rule. Or I could just write that as 18t times 3t squared minus 1 squared. All right. So now, for this problem here, what is dy dx? The idea being I parameterized both x and y in terms of t, but I still want a derivative in x and y world because I might be looking at a graph on the xy plane. My graph may not be a function, remember, but I still want to look at the graph on the xy plane. So dy dx would be the ratio of this and this. So if I write that out, dy dx would be what? It would be 18t times 3t squared minus 1 to the second all over, I'm sorry, over this, over 2t. Now, clearly I can simplify that. Okay, everybody cool with that? I can simplify this. So that would be 9 times 3t squared minus 1 squared. Okay. Now that we just did that, just so I have something to compare it to, can we put this, can I make y be a function of x? Is there any
Yes.
I can manipulate that? Well, if I look at that statement right there, doesn't that say that t squared equals x minus 2? So can I replace this with this? By the way, you may not always be able to do that, but I think in this case, that's not that bad. Do you agree? So it looks like I can say y equals 3 times x minus 2 minus 1, all raised to the third power. So that would be 3x minus 6 minus 1. So how about 3x minus 7 to the third power? So is everybody cool with that? I think that's what we have. So now let's continue. If that's the case, then what's dy dx? That would be 3x minus 7 to the second power times the chain rule factor, which would be 3, or 9 times 3x minus 7 to the second power. Okay, well, we just said that 3t squared minus 1 is equal to 3x minus 7. And look at our answer. 3t squared minus 1 squared, or excuse me, 9 3t minus 1. Same answer, isn't it? That's a good thing that it's the same answer. And which way do I go? Well, it depends. I mean, do I want to leave things in t? Do I want to leave things in terms of x and y? It's the situation will dictate that. Now, let's look at a problem that's a little more complicated that doesn't involve functions that I might easily be able to translate. So I want to go back to a problem that I do in Calc 1. This is the problem where I actually introduce implicit differentiation. Let's consider x squared plus y squared is r squared, where r is just a constant. I have a circle of radius r, nothing really, incredible there. Okay, try that again. I can draw circles, I can't draw lines. That's pathetic. Back, let me use it. Okay, let's try that. I have a point here, call it x comma y. I would like the slope of the tangent line. So in other words, I want the derivative. Problem is it's a circle. Now, I know multiple ways of doing the derivative. I can do top half, bottom half. That's what I do in Calc 1. I start by doing top half, bottom half, find the derivatives. It's a lot of work. Implicit differentiation is way faster, way simpler, and gets us the same answer. So let's start by doing this implicitly. This is Calc 1. So that means I'm going to differentiate both sides with respect to x. So I'm going to d dx x squared plus y squared. I'm going to d dx r squared. Okay, so help me out here. So what's the derivative on the left? It would be 2x plus what? Differentiating with respect to x.
Plus y dx.
Plus y?
Y squared.
I'm differentiating y squared. So how about
2y dy dx?
Yeah, 2y dy dx. There we go. That's the chain rule factor. What's the derivative of r squared?
Isn't it a constant?
So the derivative is
0?
0. Yeah. So now when I gather this, let me throw the 2x over to the other side. So dy dx is equal to negative x over y, and that's true. At every point on the circle, the slope of the tangent line is negative x over y. And by the way, there's a really easy way to confirm this. One thing we absolutely know about a radius and a tangent line at the point of intersection, we know they are perpendicular. So if this is the point x comma y, wouldn't the slope of the orange simply be y over x? Everybody agree with that?
Yep.
And how do you do perpendiculars? Don't you flip it over and change the sign? So that's, you go, oh, okay, yeah, I could have done that without calculus. You're right. But now we want to do it through parameterization. This is a little bit trickier, but this will I want to show you that you get the same results. And therefore, it never matters which route you take. We all agree that this is the answer in XY world. So the parameterization of this circle, I'm going to erase the bottom half, I need the space. The typical parameterization would be let x equal r cos t, y equals r sine t. Then when I do x squared plus y squared, I'll get r squared cos squared plus r squared sine squared, which is just r squared. Okay, this would be the typical parameterization. And of course, I want the whole circle. So I would say this. Now let's do what we just did a moment ago. Let's do dx dt and dy dt. So dx dt is, what's the derivative of this guy with respect to t? Remember, r is a constant. So that guy would be, help me out here.
That's negative r sine t.
Good, negative r sine t. Dy dt is
R cosine t.
r cos t. So dy dx is this over this. So that would be r cos t over negative r sine t, which is simply negative what?
Cotangent.
Cotangent, good. And I'm claiming that this answer and this answer are the same. Well, let's see. If I go back to my picture here, let's call that angle, actually not theta, sorry. Let's call that angle t. That's what we're doing. If that angle's t, then the cosine of t over the sine of t is the same as x over y.
Oh,
Same thing, isn't it? So in other words, it is exactly the same answer. So which one would you use? It depends. Am I giving you ordered pairs on the XY plane, or am I giving you angles? Because if I was giving you angles, this would be more convenient. If I was giving you points on the plane. But the beautiful thing is we just got the same conclusion. These say exactly the same thing in the parameterized world. So finding derivatives of parametrically defined curves is actually very simple. There's just nothing complicated about it. You find these guys and you take the ratio. That's it. I mean, there's not a lot of thought. And the reason you don't have to justify it is because we used the chain rule to get the formula in the first place, which means it's valid always. You don't have to rederive it every time you do it. So now let's look at something that we looked at yesterday. Particularly, let's look at our ninja throwing star. Because that one is eminently cool, as we all know. So do you remember what the definition was? I said x is the cosine cubed of t, y is the sine cubed of t. I would like to know the derivative. Now, I also showed you that if I said cos squared, that'd be the same as x to the 2/3. Sine squared would be y to the 2/3. Therefore, this parameterization and this equation are actually exactly the same thing. Then we also saw that the nature of the graph, therefore, looks something like this. Right, so I have these really interesting 4 points here. Oh, hold on a second, let me get rid of that. My phone is never close by. So I would like to know, what is the slope of the tangent line at every point on this curve? And then I can start looking at those cusps. So the easiest way to do that, there's two ways I can do this. I can differentiate this implicitly, and that would be absolutely correct. It might look a little scary, but it would be correct. So let's start with that one. I'm going to go d dx to both sides here. And when I do that, okay, what will I get on the left side? I'm kind of ugly, but what do I get?
2/3 x to the 1/3.
To the negative.
Oh, negative 1/3 plus 2/3 d. Yeah, negative 1/3 dy dx.
And then how about the right side? Piece of cake.
0.
So like before, send that guy that way, and I would have dy dx is going to equal negative 2/3 x to the negative 1/3 over 2/3 y to the negative 1/3. Well, that just looks horrible. Can I simplify that tremendously? Well, let's start with that. I'd probably put the y up and the x down. So what does it look like in that term? It looks like dy dx is simply the negative of y to the 1/3 over x to the 1/3, or if you want to just say cube root. Okay, in XY world, yikes, that's scary looking. And you notice, oh, these cusps here would be where x is 0, that derivative is undefined. And these cusps here is where y would be 0. And so they approach horizontal tangent lines. Interesting. Now let's do it from this point of view, because that is the whole point today. So dx dt, what do I got? I got 3 cos squared t, chain rule factor negative sine t. dy dt, I have 3 sine squared t, chain rule factor cos t. Now I'm going to erase this because I don't need this anymore. So what is dy dx? Well, it's this over this. I should get lots of canceling, shouldn't I? What will I be left with when all is said and done? So those will go. One of those will go that whole thing. One of those will go that whole thing. What does that leave me with? Anyone?
Is that just negative tangent?
Negative tangent of t. Wow, that doesn't look nearly as scary as what that one was. Negative tangent of t? Well, what is y over x right now? What is y over x?
Sine cube t divided by cosine cube t.
And isn't that the same as saying sine t over cos t cubed, which is what?
Tangent cube t.
Oh, so what's the tangent of t then? Wouldn't it be the cube root of this? Does everybody see it? This is just, if I want to write like that, isn't that the same thing? Negative tan, because tan would be the cube root of it. So it's, again, I'm verifying it's the exact same thing. But wouldn't you agree that this was a little less terrifying, a little easier to manipulate? Plus now, tangent is not defined at pi over 2. And at pi over 2 is where I have my, and 3 pi over 2 is where I have my vertical cusps. Tangent is 0 at 0 and pi. Aha. So again, it verifies. Kind of cool. So you guys could do this all day. You can all be Captain America, right? You just do this all day long. You can just take derivative after derivative, and there's just not a whole lot going on because the derivatives are not real complicated. We're not doing anything with our answers quite yet. So now the question is, what about a second derivative? What about a second derivative? What would that look like? I really don't want to do the second derivative for that one. I think it would be scary. But in general, how do you do a second derivative using this parameterization? Because that's not a trivial thing. Let me go back to my circle again. This pen is starting to die. No, we need to get back on campus soon. I'm running out of all my blue pens. Oh my goodness. All right, here's one. Okay, so same thing as we did before. X comma y, x squared plus y squared is r squared. We just figured out a moment ago that dy dx was negative x over y. Okay, I would like the second derivative. So d squared y dx squared is simply the derivative of this. I don't know if you remember, but doing second derivatives implicitly is actually one of the nastiest things you could do. In fact, we kind of avoid it like the plague in Calc 1 because it's not nice. This is probably the easiest one I could come up with, and it's still not very nice. Straight up quotient rule. So this is going to be, I'm going to leave the negative completely out. So think of taking the negative just so you don't get lost in it. So bottom times derivative of top minus the top times derivative of the bottom. I pulled the negative in front over the bottom squared. Okay. This is this. So I've got y minus x times negative x over y, all over y squared. Okay. Don't really like this. How can I deal with that most effectively? Multiply top and bottom by, oops, sorry, not 1 over y, sorry. Multiply top and bottom by y over y. Now when I multiply that y in there, I'm going to have negative y squared plus x squared over y cubed. Anybody see anything there? What's my numerator?
X squared plus y squared.
So my numerator
R squared.
It's just r squared. So my answer is negative r squared over y cubed. This is as easy a second derivative as I can possibly come up with implicitly. And that was not trivial. So that's our answer in XY world. Keep that in mind. So our second derivative, because I want to do it, obviously, the parameterized version, so we have something to compare it to. Okay. Problem is,
did you drop a squared from the dx?
Did I? Oh, thank you. Yes. I was looking down here. It fell. I caught it and put it back up. There we go. All right. I'm leaving those up there so we have something to compare to. A circle is about the friendliest shape. If you're going to do something implicitly, circle is the best one. Everything works out so nicely. But neither one of those was trivial. So now how do we do a second derivative of a parametrically defined function? It's not as easy as you think. So if dy dx equals, dy dt over dx dt, we know that. So then the question is, how do I get this? Well, clearly this means I'm going to go d dx of dy dt over dx dt, right? Because that's what it means to be the second derivative. It means I'm doing d dx of dy dx. Okay, everybody agree with that? That's what I'm doing.
Is that d squared y or dx squared? How do we know? I just want to know how do I write that?
That's the only way you can write it. Yeah. That's the only notation that's ever existed for that.
So the first one is d squared y over dx squared.
Lest we forget, this is an operator. This is considered one symbol. So if I apply this to something and then I apply that to something, it's saying I applied d squared. That's actually a way you could read that. Dx is one thing. Oh, okay. Now, it does feel redundant that you're putting the 2 on the top and you're putting the 2 on the bottom. I mean, everybody should say, why do I have to put it both times? Well, it's a Calc 3 argument, but I'll explain. The 2 on top means you're taking the second derivative. The 2 on the bottom means you're doing both of them with respect to x. So if I took the third derivative and I take the third derivative, yeah, like I could do it with something else. Yeah, almost all of your multiple derivatives would be with respect to multiple variables. So in other words, in Calc 3, you're basically going to have a dx and a dy on the bottom. You might have a d4 on the top, and 2 of them are x's and 2 of them are y's.
Oh, I see.
All derivatives are going to be with respect to multiple variables. So what feels redundant in Calc 1 and 2, and it does feel redundant. Do I really need to put it twice? Actually, yes, because they say something completely unrelated. Two derivatives with respect to x, because it doesn't have to be with respect to x for every derivative in the future, because everything after this class, every time you take a derivative after this class, it will always be with respect to multiple variables, and you have to indicate how many you're doing with each variable. Don't worry about it. By the way, that is the right question to ask, because most people just say it feels like I'm repeating myself, but you're saying slightly different things, and it has to do with the ddx is considered a single symbol. So when I repeat it, that just says how many times I'm repeating it. Because what we're going to do next semester is I might have a ddx and a ddy in the same problem, and a ddz in the same problem. Oh my gosh. Yeah, but that won't bother you. So our problem here is there are no x's in here. I have a dy dt and a dx dt. There's only t's. So how do I do this? Well, I'm going to redo this. I'm going to restate how we're doing it, because the trick is in the notation. Okay, the trick is in the notation, and it has to do with where we're doing stuff. So if I go back and say, okay, what exactly did we do when we did? Let's go. I'm just going to write the first derivative right now. Okay, dy dx is clearly d dx of y. That's what it means. I'm doing the derivative with respect to, I remember what I wrote. And we know that's dy dt over dx dt. But I'm going to rewrite it a different way. I'm going to write that as d dt of y. Now stare at that for a moment. Is what I wrote still exactly the same thing? dy dx is d dx of y. dy dt is d dt of y. And therein lies the trick. It's the same y. So here's what I want to do. I want to do d dx of that. So the second derivative is d dx of that first derivative. It's d dx of dy dx. Okay, which was d dx of y. But that means it's going to then be this formula that we just derived says when I do d dx of a thing, it's the same as doing d dt of the thing over dx dt. That's what we're saying right there. I did d dx of y, it's the same as doing d dt of y over dx dt. Now I want to do d dx of dy dx. It's the same as doing d dt of dy dx over dx dt. And this is the trick. This is the formula. In fact, some textbooks don't even do the derivation. They just tell you that that's the answer. That's the second derivative. Oh, it's not as trivial as we thought it was. There's actually a little bit more involved. So we'll do a couple of examples. Okay, so once I find my dy dx, which by the way will be in terms of t's, I can do this. So let's erase this up here. And by the way, I do have posted notes where I go through this in tremendous detail, by the way. We'll do a simple one here. So x is going to be, let's say, t cubed plus 2t, and y is going to be, I don't know, t squared plus 1. Let's keep it really simple. dx dt is 3t squared plus 2. dy dt is 2t. Let me erase, I don't need this anymore. All right, so what is dy dx? This over this. Now, what's the second derivative? The second derivative, same denominator, but what goes on top? The derivative of this. Because I said your dy dx will all be in terms of t because we're doing the parameterized version. So this is what my second derivative will look like. Okay, that's actually not that complicated. I just got to remember the order of things. So let's do this derivative. So it'd be bottom times derivative of top minus top times derivative of bottom over the square of the bottom all over that. Okay, and I can clearly simplify that. I'll put it over here. Well, the square of that over that means that I'm going to have a 3t plus 2 cubed on the bottom. That looks like minus 12t squared. So it looks like a minus 9t squared plus 4 on top over this. Now, there's nothing about the answer that's particularly important. It was the route to get to the answer. So if we understand how to do this, this is going to be trivial 100% of the time. But now the second derivative, I include the exact same dx dt, but I have the derivative of the first derivative in my numerator. This is not the usual XY world. This is the parameterized world. Okay, before we move on, any question on this? It's a formula. I just derived it, and now we're just going to use it every time. Not a whole lot of thought necessary. Again, in the posted notes, I've gone into some great detail on some of these. Now let's go back and do the circle again. You're going to like this because it's so clean. So we did the circle a little while ago. We said let x be r cos t, y is r sine t. We got dx dt is negative r sine t, dy dt is r cos t. Okay, we already did this. Then we stated our derivative. Our dy dx is simply the ratio this over this.
Are we still doing the same problem with different method, or is that?
Well, no, we're now going to do the second derivative. So this was negative r, excuse me, not negative r, negative cotangent. All right, this is where we left off before. I now want the second derivative. Does that make sense?
Okay.
Now that we know how, the second derivative is going to be dt of that over that. Okay, everybody cool with that so far? I didn't mess anything up. I think this is what we want. Now, what's the derivative of the negative cotan? Yikes. The negative cotan, what's the derivative? Anybody know?
Cosecant cotangent.
Yeah. No, it's negative natural log
Oh,
of
cosecant squared.
cosecant cotangent.
It's cosecant
But
squared.
that's integral.
Oh boy, the derivative of the, if it always helps, what's the derivative of the tangent? It's the secant squared. So the derivative of the cotangent involves the cosecant squared.
Right.
You got to remember. So this would be positive cosecant, ooh, that's a terrible S, sorry. Positive cosecant squared over, now, isn't cosecant the reciprocal of sine to begin with?
Yeah.
Yeah. So can I improve upon this? I can either move the sines on top or the cosecants on the bottom. For now, it doesn't really matter. Usually we say, no, I don't want a quotient, but I kind of want it to look like my first answer. That's why. So if I put the cosecants on the bottom, which again is not great form, then it'll be sine to the What power?
Cube.
Okay. So right now we've got that this, I'll put it right here. Okay. Right now we've got that the second derivative is -1 over r times the cube of the sine. Just for fun, I'm going to multiply top and bottom by r squared because it's fun. Now I've got -r squared over r cubed sine cubed. Why would I do such a thing? Because now I can write my bottom as r sine t quantity cubed, thus making it -r squared over y cubed. And isn't that the result we got in XY world? Right? You should be celebrating and rejoicing. Again, I want to confirm that we get the same answer. This version, any version of this is the right answer, but how do I make this look like when we did it in XY world, we got -r squared over y cubed, if you remember. So I just did a little manipulation algebraically to show you it was the same thing. I wouldn't need to do that. I can just leave it in the trig form. So the first derivative parametrically should never cause any issues ever, no matter what the question. There's just nothing going on. Second derivative, you just got to be a little more careful because I'm taking a derivative of the first derivative, so I got to get it right. But just doing this is actually quite simple in general. You're never going to need to take a higher derivative. Okay, first derivative, second derivative, that's it. Okay, any question on this? We're going to move on in a moment. This is how you do it. We've learned different forms of differentiation, such as implicit, right? Once we know all of our derivative formulas, we have over 20, then we say, okay, how do I do it implicitly? Where does chain rule figure in and all these kinds of things? So here's how we do it if it's parametrically defined curves. And you wouldn't choose to do this unless it made things easier. Because what if I have a curve that is not a function, like a circle, like an ellipse, like a hyperbola, like a figure eight? What if I have something like my ninja throwing star, but I want derivatives? Doing those in XY world not only requires implicit differentiation, but can really result in some nasty algebra. But we've already shown today that, you know what, when we do this in parameterized form, the algebra was way simpler. Okay, if you just have a regular function, y is a function of x, no, there's no reason to parameterize. But if it's not a function, parameterization definitely makes things easier. Now I want to move on to arc length. So what I'm going to start with is reviewing what you learned in Calc 1, because we're going to segue and then do our version of what we need. And then we're going to do this again in Calc 3 when we get to 3D. This is the only topic that you actually do all 3 semesters. So it's considered kind of important. So the concept of arc length is this. All right. I have this point here, let's call it x naught, y naught, and I'm ending at this point here, let's call it x1, y1. Oops. And I'd like to know the length of the curve. It's actually that simple. And what I do if I'm in the classroom situation, I'm standing in the front of the room and I'll actually just start walking through the room to get to the back door. But in doing that, I've got to weave in and out of desks. So if I said, how far did I travel? Well, the crude estimation would be, well, let me just start with that. If I just calculate the distance between those 2 points, which is trivial, right? Distance formula is baby algebra. Is that a good answer? Is that a good answer?
Well, it's not a right answer.
It's not very accurate.
It's not a very accurate answer, but it's a starting point. I know I have to travel a little bit further than that. How much further? I don't know. But
can we?
I have to travel a little longer than that. Agreed?
Can we take the integral from x0 to x1 of the function, and that would equal the distance?
Now the problem, if I integrate the function, that's going to give me the area under the curve.
Oh, okay. Because I was thinking.
Now, distance formula we know. I just did a line segment from one end to the other, and you guys agree that's a really rough estimation, but it's too low. How would I get a better estimation?
If you divide it up into smaller,
more cowbells. I mean, more line segments. Got it? You agree? Mm-hmm. What if I did that instead? And that would be better.
Yeah.
Agreed? You guys smell it? Smells like a limit, doesn't it? Oh, yes. Lots of line segments. How many line segments? infinitely many line segments. How long are they? But if we can set it up that way, then we can have an integration. But it's not the area under the curve part. So what I want to do is I want to just take one little piece of this and I'm going to blow it way up. I'm taking one of these, I'm blowing it hugely up. Now, clearly I've got a right angle there if I do it this way. Now the formal notation, we're using what's called differential notation. I wasn't there when we decided, but universally, does anybody know what symbol we always use for length of a curve? It doesn't matter, 2 dimensions, 3 dimensions. We always use the same symbol for our curve.
S.
S. Well, we use M for slope. I mean, it's, why we use S, I don't know, but it's universal. Whenever you see S, you know it's going to be arc length. So the actual change in arc length is this. The actual change in X is this. The actual change in Y is this. When we're using the line segment to estimate the actual curve, that's called the differential. And that's where you, if you remember the line segment leaving the curve, remember you use the value on the line segment, the tangent line, to estimate the value on the curve. The notation we generally use is called the differential notation. So the change on the line segment, we use the D, the actual change, we use the delta. So in this picture here, delta X and the DX are the same, because that's the same change of X, whether I'm talking about the line segment or the curve, and that's the same here. So the whole point in this problem is to estimate delta S with ds. This is the formal correct way of saying it. Delta S cannot equal ds. That's impossible. But if I take the limit as these get smaller and smaller and smaller, obviously delta S and ds get closer and closer and closer together. So let's do the calculation. This is just simply the distance formula. All right. So look at my picture. It's a Pythagorean relationship. So I'd have delta X squared plus delta Y squared under the square root. Does that make sense, everybody? That's exactly what the length of that line segment is. Pythagorean theorem. So now what I want to do is I want to factor. So I'm going to off to the side. If I had something that looked like this, and I said factor out the a squared, how would you factor out an a squared? You've done this math before. What would you be left with?
1 plus b over a squared, b squared over a squared.
Yeah, that's not that hard. I want to factor out a delta x squared. So that means I want to have a 1 plus delta y squared over delta x squared all times delta x squared. I'm going to put it on that side, but it's all under a square root, isn't it? And since delta, by the way, the change in y can be negative as I go up and down, but the change in x is always positive because I'm moving left to right. So I can pull this out and I can write this then, how about as 1 plus the square of delta y over delta x, all times delta x. Ah, okay, you with me? Now, if I said, let's add them all up, I'm going to erase this.
Professor, when you first wrote delta S and the squiggly lines, do you mean no here? Yeah, does that mean they're asymptotic to? This
is being estimated by this. They're asymptotic. Remember, squiggle becomes equal when you take a limit. Think of the going the other way, like the tangent line leaving the curve. It's equal when I take the limit. I'm going to take the limit. So let's first add up all the line segments. If I add up all the length of the line segments, then we can say that the actual S can be estimated by the sum I equal 1 to n. Now I'm going to do this. I'm going to write it like this: 1 plus delta yi over delta xi. That's the ith. So technically these can all have i's on them. Squared delta xi. Okay. This should look kind of familiar. Not the actual numbers, but the form. You go, oh, and what does S equal? It equals the limit as the norm of the partition approaches 0. That's verbiage that I hope that you kind of relate to and remember from way, 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 way back when. And we know this is going to equal a definite integral at some point. This is called the Riemann sum. Tricky thing is, what definite integral is this going to equal? Because it doesn't look like anything. So here's the coolest part. The next thing I'm going to show you is the single most important part of all the development of this. And unfortunately, none of this is in any textbook. It's not in any YouTube video. In fact, you're not going to find this anywhere. Every textbook just says, and here's the answer. And you'll say, how did you go from there to there? Because there's no way you can write an integral. There's nothing that looks like this. I mean, I have deltas. I mean, what does that even mean? So what we do is, I'm going to show you what you already know. Don't we know that the limit of a sum is the sum of the limits? Do we know that? The limit of a sum is the sum of the limits. Is that one of the more important limit properties?
Yeah.
Yeah. So I'm going to pick this limit up and I'm going to stick it inside here. The limit of the square root, isn't that the square root of the limit? The limit of a function is the function of the limit. So I can move that limit now inside the root. So I have the limit of 1, which is 1, plus the limit of this thing squared. Well, wouldn't that be the square of the limit? You with me so far? This is absolutely equal to the sum from I equals 1 to n of the square root of 1 plus the limit as the norm of the partition approaches 0 of delta yi over delta xi, all being squared. That's what I'm pointing at. I can move the limit all the way into there. Remember, the norm of the partition would be the largest such delta x. Remember, if the biggest one's going to 0, then all of them are going to 0. But because I moved this all the way to the inside, this is the only delta x I see. So this statement right here is the same as just saying the limit as delta x approaches 0 of delta y over delta x, and I'm adding them all up. That looks vaguely familiar. How about if I wrote it this way? This is the exact same thing. If I'm using x and y notation, delta y. If I'm using function notation, this is the same as delta y. Does this statement here look vaguely familiar to anybody?
Is that the chain rule or something?
Earlier, it's the definition of the, starts with the D, ends with an derivative.
Derivative.
That is the, not a. That's the only one that's ever existed. That's the definition of the derivative. These say the exact same thing, right? If I use function notation or I use this notation, in other words, what does this equal? It equals dy dx, or it equals f prime of x, depending, did you use function notation or did you use xy notation? This limit is dy dx. So why am I pointing that out? Because that's where the formula comes from. After all of this, we know this is an integral then. An integral, let's just say from A to B. In my picture, I think it was x0 to x1. I'll use those numbers. In my picture, I said, starting x value, ending x value, but what is my integrand? 1 plus the square of dy dx integrated with respect to x. And this is the arc length formula you learned in Calc 1. But I'm guessing if you're like most Calc 1 students, you were just told that formula. You never saw any portion of the development because no one ever does, because most people actually have, by the way, including authors of textbooks, they actually have no idea where it came from. They just know it's true. I just showed you exactly where it came from. This is Calc 1. So if you were in my Calc 1 class, you saw everything I just did. Why did I show you all that? Because we're going to do the same thing, but now parameterized, because it's more useful in this sense. Now, the problem with this, every calculus book has arc length formulas, arc length questions in the first semester. And the questions usually look like this. Set up the integral to find the length of the curve from here to here. Set up the integral to find the arc. They rarely say find the arc length. Because of the infinitely many functions you could write in here, you can almost never integrate this. There's only 3 functions that exist that you can actually integrate in Calc 1. 3, that's it. Of the infinitely many functions you could write, let's keep it really simple. Let's just say, let's just say dy dx or y is just a really simple polynomial. Maybe y is x cubed or y is square root or something. Well, the moment I take the derivative and then I square it and then I add 1 to it, I won't be able to evaluate that root and I won't have a chain rule factor, meaning that most integrations, all you can do is set up the integral. You can't actually finish them. So it's kind of frustrating. But we're going to parameterize, which will automatically open up many, many, many more problems that will allow us to do things that we might not be able to do in XY world. So how am I going to do the parameterization? Well, let me go back now. I don't have to do all of the same development anymore. I did this to remind you where it came from, even if you never saw it in your Calc 1. It's unfortunate, but most people never actually see this. They just are told the formula. Same thing with things like surface area. You're just told the formula. You don't know where it came from. Let's go back to our picture. Okay, that was my delta X. That was my delta Y. That was my delta S. That was my ds. So we know that delta S is estimated by ds, which is delta X squared plus delta Y squared, yada, yada, yada. All right. I'm going to do the same thing I did before, but slightly different. If I had the quantity A squared plus B squared, I want to factor it. Okay, we did that before. We factored out A squared. Yeah, I know how it works, Mr. Brown. No, I don't want to factor out A squared. I want to factor out C squared. Can you do that? Well, as long as C is not 0, you can. How do I factor out C squared?
Just do A squared divided by C squared plus B squared divided by C squared.
Oh, everybody cool with that? That works. So guess what I want to factor out of that? I want to factor out not a delta X squared. I don't want to factor out a delta Y squared. I want to factor out a delta T squared. So this would equal delta X squared over delta T squared plus delta Y squared over delta T squared, all times delta T squared. Okay, you with me so far? But all of that lives under a square root. So I'm going to rewrite this as delta X over delta T quantity squared plus delta Y over delta T quantity squared, all under the root and the delta T on the outside. Huh. Is this way different? No, before we had delta X squared, delta Y squared, delta X. I am now introducing the parameter T. Algebraically, these are absolutely the same. That's not even a question. Geometrically, it's kind of tricky because I've introduced a new variable, but I know this is true. So now I can say S is, and I'll do the same thing, limit as the norm of the partition approaches 0 of the sum from I equal 1 to n of this. And I'll put my little subscripts this time. Okay. But the nice thing is you guys now know what's legal. You know now that I can move the limit inside, 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 and this will equal an integral. Let's just say, for lack of better terms, from T0 to T1, because I have no idea what the values of T are. We have to figure that one out or be told it. But what's my integrand? What will these become? As delta T goes to 0 of delta X over T, won't that become dx dt? Everybody see it? And what will this guy be? dy dt integrated with respect to T. And this is the parameterized Archway formula. And all I did was use the exact same reasoning we used a few minutes ago, but now with the parameter. The idea being that if I had a function that, first of all, maybe it's not even a function. Okay, maybe it's a circle or something. But if I do this, that's kind of interesting. Let's do a good one. All right. Now you guys remember, hopefully in Calc 1, you did things like you took a semicircle and then you rotated it about an axis. In other words, you created a sphere, and then you used the volume formula that you generated or the surface area formula, and you actually came up with the volume of a sphere. You came up with the surface area of a sphere, and you go, that's so cool. And then you realize it's the only way you can actually come up with those formulas. We've been told all these geometric formulas our whole lives. We just never saw them in play. Turned out all of them required calculus. That's crazy. But there's so many things that you know. You absolutely know things like the area of a circle. Everybody knows that. And I'll say, well, can you show me why the area of a circle is pi r squared? No, you can't, not without calculus. Oh, so how about, I'd like to know, what is the circumference of this circle? Well, I know the circumference of a circle. Somebody told you the circumference of a circle. Can you prove the circumference of a circle to me? Probably not. Well, maybe you can. Let's without any prior assumptions, let's parameterize this. So let's let x equal r cos t, y equals r sine t, and this one's really important. T range from 0 to 2 pi. Why is this more important now than it was before even? Where do you think that's going to show up in the problem?
As the, for integration, what's it called, from 0 to 2 pi?
The limits of integration.
Thank you.
Oh, because t equals 0 puts me here, pi over 2 pi. Those will be my limits of integration. So I said, when you're going from a t value to another t value, you either have to be told what it is, like I'm doing here, or you can figure it out. That's this part really is not the hardest part ever. So what is dx dt? We've done this before, but now we're going to do it from a different point of view. We were just doing derivatives before. So dx dt is negative r sine t. dy dt is r cos t. So the next thing I need, what is the square of dx dt plus the square of dy dt? By the way, are we making any assumptions whatsoever? No, the only assumption we're making is that the Pythagorean theorem, the cos squared t plus sine squared t is 1, which we prove. I proved that on day one, first 15 minutes of Calc 1. I proved that one absolutely. I don't tell anybody that. So we know the Pythagorean identities because they come from the Pythagorean theorem. That's not anything that's in question. I'm not using any facts whatsoever about a circle, except that this is a simple parameterization because I know that this squared plus this squared, right, will end up equaling r squared, and that's beautiful. So when I do this, I'm going to get r squared sine squared t plus r squared cos squared t. I wanted it all under a root. Isn't this r squared times sine squared t plus cos squared t?
Which equals 1.
But that's just 1. So I have the square root of r squared, which after all that is just r. Okay. Now, with absolute certainty, because I proved it, I don't have to prove the arc length formula. It's absolute. It's absolute in every conceivable way. It's valid. The one thing I can't always do is I can't always integrate. I can always state this integral is equal to the arc length, but I may be at a dead end. I mean, I can come up with an infinite number of problems that I can't integrate. Okay, so what do we got? We have the integral from 0 to 2 pi of r dt, which is rt from 0 to 2 pi, which is 2 pi r. Oh my gosh. There it is. That's it. That's how you get the circumference of a circle. We just did it. You were told it before. Now you know where it came from. It had to come from calculus. You can't get that answer by just trial and error. You know, let me just measure my circle using my ruler that bends in a circle that has little pi markings all over it and stuff. Well, now you got to admit, that's kind of cool. We just found the circumference of a circle using the arc length formula we just derived. Could you have done this in Calc 1? Yes, but it wouldn't have been the same problem because in Calc 1 we would have done, okay, let's solve for y and let's do the top half of the circle and we'll do all the derivatives and then we'll just double the answer at the end. That's legal, but I mean, that's what you would have done in Calc 1 because you couldn't do the whole circle. It's not a function. But when I parameterize it, x and y are both functions of t. This is one of the benefits of parameterization, like I mentioned yesterday. If I take something that's not a function, the x and y can still be functions of t, which means their derivatives are usually fairly simple, which means this is much, much simpler than it was in Calc 1. So as a sort of a general rule, a parameterized arc length is usually easier than the Calc 1 version, usually. It's not an absolute. But the other thing is I can do a lot more problems when I have parameterization than I could have done last semester. That's kind of neat. Anyway, there are posted notes on this where I do a few different examples. So hopefully you can follow along. I'm going to stop here